Our last speaker for this morning session is Benno Berg from the University of Amsterdam, who will speak about algebraic structures for modified realizability.
Yeah, so thank you. Thank you also for the invitation to be here. I mean, it's my first time in Padua.
First time.
It's the first time I'm here. I mean, I attended the CCC sort of online, where I gave a very similar talk. So the idea of today is basically give that talk, but now with fewer mistakes. We'll see how that goes. So basically what happens is that I had a student already a long time ago who worked on some toposes for modified realizability. The student left academia, and so it was basically left to me to write it all up. And then when I was sort of trying to write it all up, I thought, I mean, maybe it's nice to have a sort of more general framework for constructing realizability toposes. And I was sort of reminded of the work by Alexander on implicative algebras. So I tried to put that into that framework, and so it didn't quite fit. So last time I used sort of what Alexander calls quasi-implicative algebras, but actually I think the quasi-implicative algebras also don't quite work. So so what I'm basically going to do is I'm going to present a weakening of Alexander's notion of an implicative algebra, which is a kind of algebraic notion which generalizes certain kind of algebraic structure that you can use to construct toposes, triposes, and sort of supposed to capture both triposes that come from maybe locales, depending algebras, as well as the examples coming from realizability. So that's basically what I'm going to talk about. So basically the talk will consist of a few parts. So the first part I will basically first remind you what implicative algebras are. Then I will present my weakening, and then I will sort of explain how I think using this particular weakening of these implicative algebras, you can give an account of modified realizability. So that's the plan. So in the meantime, I mean, I have another student, Marcus Briet, who is writing his master thesis with me. Hand in a couple of weeks. And he's basically checking my proofs, and then when he hands in, it's my turn to check his proofs again. So this is my hope is there. So the process should converge at some point. The truth. So yeah. Oh, maybe it's a bit slow. Oh, because I'm pressing the wrong button. Okay, yeah. So basically, first, Alexander's definition of an implicative algebra. So it basically consists of sort of two steps. So first, we define an implicative structure. So it's supposed to be an algebraic structure which generalizes, say, the notion of locale. But so we axiomate, so it's a complete flow set, and there's and consequently a binary operation which we think of as giving some sort of notion of implication. So one thing I think is actually very nice about this is that actually it axiomatizes things in terms of the implication, which I think is sometimes I have a better intuition for what the implication should be than what some of the other connectors, for example, the application should be. But okay, that's a side remark. So it is an operation that we think of as some sort of notion of implication. You should think of like the implication as the implicit complete Heiting algebra. So it is this notion of implication is monotone in the second component and antitone in the first component. And then there is this important axioms, which basically says that this implication sort of preserves arbitrary means in the second component. Oops. We should think of these elements in A as sort of truth values, or maybe as bits of evidence. Then I think it is so. So I think this ordering, it's not really, we don't really think of it as some sort of notion of logical consequence. I think that's maybe the most initially confusing part about it. But I think of it as some sort of, if you think about the elements of this implicative structure as sort of bits of evidence, then maybe something is just more evidence than something else, provides more evidence than something else. So we could call it the evidential ordering, or someone calls it also the subtyping ordering. But let's call it evidential ordering, so something just provides more evidence than something else. Then the other thing that we need to specify is which bits of evidence or which truth values we think of as the true ones, those which are actually true, or which bits of evidence are actually conclusively established a certain kind of statement. And for that we use this notion of a separator. So this selects within our implicative structure the bits of evidence that we find conclusive. And they satisfy some logical axioms. So for example, this upwards closed in the evidential ordering, and it is closed under a notion of correspondence. And then there are two sort of principles, K and S, that we hold to be true. And K and S are these principles. So A plus B plus A, and A plus B plus C, then A plus B plus A plus C. My notion of implication associates to the right, so it's the standard convention in type theory, for instance. So that's the notion of a separator. And then if you give me an implicative structure together with a separator, then we call it implicative algebra. So examples that we can think of are something like a complete hunting algebra with like a distinguished filter. So the filter would correspond to the separator. And another example, so that captures sort of localic examples, if you want. And another example is, for example, this coming from realizability. So if you have a total combinatorial algebra, say, then we could look at the subsets of this total combinatorial algebra, order those by inclusion, and then with this particular notion of implication, so one subset implies another subset, if that is the set containing all those Z, such that if we give it an X, then this expression lands in Y. And then this particular separator that we get is the one formed by all those inhabited subsets. So that is another example of the implicative algebra. Right, so crucially, implicative algebras are sufficient to construct triplexes, and as we all know from triplexes we can construct topleces.
Sorry, could you go back 1 second to the example? Did you say you take subsets of the complete algebra? You could also take elements, right? No, these are two different examples. Okay.
Yeah, so the elements in A are subsets, and then I have to select those subsets which are all to be true, and those are which bits of evidence I found conclusive. And a bit of evidence is conclusive if it has an element, if there is some evidence in it. So this is the definition of a triplex. I don't think I have to spell this out. So how do we construct triples from implicative algebra? So for that, we introduce another ordering, which we would call the logical ordering. So what you can do is, if you have an implicative algebra, you can define a new order on this implicative algebra, which is called the logical ordering. So A logically implies B. That is the case if you look at the statement, which is this implication. So that for that we have sort of conclusive evidence. We have conclusive evidence for the implication A implies B. So this defines different ordering on the simplificative algebra, and with respect to this ordering, it's actually pre-order. This structure becomes a pre-Heinting algebra, in which the implication is indeed given by the implication. So it's clear. So this is more generally, if you give me an implicative algebra and a subset, then we can look at the functions from that set to the implicative algebra. Those you can give a structure of an implicative algebra as well. Implication and order are just given pointwise. And then we have this uniform separator. So we also should give it, so we will say that a certain function from X to the implicative algebra A belongs to the uniform separator if basically the intersection or the means of all these elements phi of X belongs to the separator. So we're not saying that phi of X belongs to S for all X. We're saying that sort of uniformly, so basically that the big mean over all of these phi of X's actually belongs to the separator. So if you just done that, if you let the X vary, then basically you get a triples, which we can call the implicative triangle. So Alexander has actually shown that basically, if you then every topos that you can get from A triples can actually be obtained in this particular way. It can be obtained as associated topos of an implicative triples. So in that sense, there is no real need to generalize this notion. So in some sense, we can obtain all triples this way. Nevertheless, I think there are many naturally occurring examples that actually are not quite implicative algebras, but are something weaker. And also, there are certain kind of constructions that I would like to perform that don't quite work on implicative algebras, but work on something weaker. I don't know. I mean, I don't know how to call this weaker thing. You've decided for the moment to call these things arrow algebras. If you have a better name, then let me know. So, arrow algebras. So what is the difficult or the problematic aspect of an implicative algebra? What is it that we want to change? So, for me, the difficult bit is the preservation of means in the second component. So that was already part of this notion of an implicative structure. That is a bit too small. So what are we going to do? So we're going to drop it, and we're going to replace it by something else. So if you look at this requirement, let me see. So so I guess only one implication is really informative. So I guess it's probably this one. So on one inequality, basically. So I think the other one just follows from the fact that, means are means. So basically what I'm saying I'm going to do is, instead of requiring this for the evidential ordering, I want to have this inequality for the logical ordering. So instead I want to say something like this implies that should belong to S or something like that. That's the first approximation, and then there's some slight sort of another modification I want to make. I don't want to require this for arbitrary sets B, but only for sets B whose elements are themselves implications. So this may be where B is a collection of all elements in B are implications. So also for C implies D for some C. So that's basically my definition of an arrow algebra. So formally, so again, we can define, oops, I've done this thing I shouldn't do. This little thing is a bit hard to navigate. There's so many buttons. Yeah, thanks. So basically an arrow structure is again a complete concept with a notion of binary operation, or indication, monotone in the second, and antitone in the first component. And then a separator on such an arrow structure, okay, let's say arrow structure here, is basically a subset which is again upwards closed on the monosponents, and then should contain the combinators A and S, as before, and also a new combinator which I call A. I don't know, I just think that better. And it's basically, it's basically this. So if you take this thing over here and you take the big supremum of, the big infimum over all A's and B's, that is this combinator which I call A, and this combinator should also belong to the separator. So that is my condition on the separator on an arrow structure. So then an arrow algebra is basically an arrow structure together with a separator like this.
And we have that once more.
So I think you have to be a bit careful about the scope. So this one has scope this whole thing. This thing has the scope this whole thing. And the scope of this thing is just the whole expression. But I mean, the way to think about it, I think, is we take Alexander's definition of like preserving means in the second component, and then we just only require that sort of in logical sense, and then only for sets B which contain implications. So that's it. So, and then the point is that this is again still, so what do we want for this arrow algebra? So it's a genuine weakening. Every implicative algebra is also an arrow algebra, and we want still to be able to construct triplexes in exactly the same way. So what is it? Actually, this happens in exactly the same way. So we can again define a new, sort of like a notion of like logical ordering by just saying that the elements should belong to the separator, and then in exactly the same way as before, we can construct a triplet, so nothing changes. The proof changes, but the statements themselves don't change. The proof is a bit more complicated. So why would I want to have this particular weakening? So one reason for weakening is that we could only construct implicative algebras from total combinatorial algebras. And I also want to construct implicative algebras from partial combinatorial algebras. So Alexander has this notion of a quasi-implicative structure, which does the same job, but as I will say, I will point to the place where I cannot use the quasi-implicative structures anymore. So by PCA in this setting, I can actually mean something like a relative ordered PCA. So if you follow the philosophy of Jaap's students, like Peter Holstein, Jesse Zoethout, they have been sort of thinking more in terms of PCAs as something like, well, basically one PCA sitting inside another PCA in a nice way. So we can construct, and then there's an ordering relation as well. So we can construct arrow algebras in that setting. So in a way which should contain no surprises to people who know this area. So I just flashed the definition. So for example, Yetzin's PhD thesis calls a partial implicative poset is just a poset together with a partial binary operation, and this domain of this partial binary operation is downwards closed, and it is also like monotone in on its domain of definition. So we could call such a partial predictive subset total, and the ordering operation is total, and discrete. The ordering is discrete. So some examples of things which actually become PCAs. So one additional example is K1, so the set of natural numbers with Pliny application. So we've already seen that a few times. So one natural number applied to another natural number is the outcome of the nth Turing machine input n, whenever this is defined for some enumeration of the Turing machines. And we can take discrete ordering. If you want an example in which the ordering is not discrete, you can take terms in the lambda calculus and say that n is less than or equal to n if n beta reduces, notice that beta reduces to n. So then they have this notion of a filter. So it's very similar to that of a separator. So a filter is a subset, it's like a sub-PCA in some sense. So it is a set of elements which is closed under the application whenever defined, outwards closed in its ordering. And again, there are these elements K and S which satisfy these conditions, which I think are very standard. So then the idea is that, so you could say partial ordered relative or algebra, let's just call it PCA, is a partial multiplicative closet together with such a filter. And then you can construct an arrow structure or an arrow algebra from such a PCA. So we just look at a collection of downsets of the PCA and define this particular notional implication. So one subset downset implies another downset. That's the downset consisting of those elements Z. So that for every x applied to Z is defined, and x applies to Z belongs to 1. And then we can take very not be inhabited subsets, downsets, as those belonging to the separator, but those downsets that contain an element from the filter that defines a separator. Actually, there is another arrow algebra that you can define from a PCA, which is also quite nice. Also, that you can, as an example, I think this paper observes that. So instead of just taking all the downsets, you can also take the pairs, if you want. So the partial equivalence relation. So you could say the subsets, or the subsets of, well, this should be the subsets of p squared, so p times p, that are downwards closed, symmetric, and transitive, that also contains like an arrow structure. So the arrow structure is basically given as follows. So one, okay, we can read it. How much time do I have? Oh,
at least 10 minutes. At least.
10. I was scared. Approaching me.
It was not 14.
No, okay, that's right. Okay, that's good. So that's basically we take the pairs such that for every pair in X, so the component-wise application that should be defined, and then the component-wise application should be multiplied. And then you can take those things that there is a pair, a separator you can take for those things that contain a pair which are both components belong to the filter. So this is another example of an arrow algebra. And then of course we know that we can take the associated tripulses and then topulses. So you do that of course in the first case, you get the realizability topulus associated to PCA. If you do it for this, you get something like the extensional realizability topulus associated to that PCA. Okay. So another reason for weakening this notion of implicative algebra is because I wanted it to be closed under a particular kind of construction. So this is basically a kind of notion of like a nucleus or a local operator for a particular, so I think this is what corresponds to the nucleus in locale theory. So we want to have something like a nucleus for arrow algebras as well. And it's just, so we could define it to be a mapping, so we fix some arrow algebra, and a mapping from that arrow algebra to itself. Could be called a nucleus if it is monotone, in this sense, for the evidential ordering, and then it satisfies sort of these like monad rules in the sense of the separator. So that is, yeah, so that's the notion of nucleus. And then it's quite, there's an easy construction of constructing a new arrow algebra from an old arrow algebra together with such a nucleus, and we can do it like this. So we just define, we take the same set, we take the same evidential ordering, but we define a new implication. So A, J implies B, if A implies G of B. And we define a new separator. We say that A belongs to the new separator if J of A belongs to the old separator. And this is again an arrow algebra. And I don't think this works. At least, was it? I don't know. No, I don't think this quite works. No, I don't think this works for quasi-elliptic algebras. This is one of the mistakes in the previous talk that I give. And it also doesn't, also here in fact, so this, you could maybe ask the question, like, why have you insisted on the fact that all of these elements in B should be implications? Where does it come from?
Why?
Yeah, so if without, so the first argument is the reason why I do this is that, first of all, the argument, the example coming from PCAs is would no longer, doesn't satisfy this, this law if I say that the elements of B can be arbitrary. So I lose the example coming from PCAs. It's a bit of a subtle thing, and it has to do with the fact that sort of the application is partial, but in some cases it actually is defined. I can say more about it maybe in the Q&A. And another reason for doing this is that I think also I don't know how to prove this proposition unless I make this particular requirement. So I wanted to say something about modified realizability and how different sources for modified realizability can be understood once we have this sort of machinery for arrow algebras. So for me, modified realizability, I think that's what the Topos theoretic account basically gives us, or tells us, is that with modified realizability there's like a distinction between potential and actual realizers. Every actual realizer is of course a potential realizer, but not necessarily the other way around. And the crucial ingredient is that every proposition, including falsity, has at least one potential realizer, but of course no actual realizer. And we consider something to be true if it has an actual realizer. So this sort of combination of ideas, I think, was extracted from sort of Toolstad's writings and then turned into a topos by Grayson, and I think also Hyland is probably quite influential in this. That's the exact history. But so how can we do such a thing in the language of arrow algebras? So if you give me an arrow algebra, I can construct a new arrow algebra where the elements of the arrow algebras are just pairs. XA, XP, where XA is less than or equal to XP in the evidential ordering. So where XA of course stands for actual and XP stands for potential. So we have actual evidence and potential evidence, where the actual evidence is less than or equal to the potential evidence. This often is an arrow algebra. Maybe this result is not quite true in full generality, I don't exactly know. But in the cases of interest, it will become an arrow algebra. If we order the pairs pointwise, we define a new implication like this. So we basically do the pointwise implication, but then we have to make sure that this thing over here is less than or equal to that thing in the evidential ordering. So we take the evidential means of the two things. And then we'll say that an element such a pair belongs to the separator if the first component belongs to the separator. So this is some kind of Sierpinski construction, if you want. And then we can define a nucleus on this, where we take, so in general, for any nucleus, for every implicative, every arrow algebra, if you give me an element in this arrow algebra, you can look at the operation which takes the join with that particular element, but now it's the join in the logical ordering, and that will give you a particular example of a nucleus, just as in locale theory. And if we take the join with this particular element, so bottom in the first component and top in the second component, we get a nice nucleus, and the resulting arrow algebra that we get with respect to this nucleus, we can call the modification of this particular arrow algebra. So the traditional real modules, usually called modified realizability topos, is actually one you get by doing this particular construction when you start with the good old-fashioned arrow algebra for number realizability, so that's just subsets of K1. If you then do this multiplication construction, so from the previous slide, on this arrow algebra, you get an arrow algebra for modified realizability topos. So what I wanted, but we can actually also do the exact same construction for these pers. So pers over K1. And then you get a topos which has some features of extensional realizability and some features of modified realizability. So we get an extensional modified realizability topos. So this is not fully checked, but I believe that it is correct. And one thing I'm hoping is that in this extensional modified realizability topos, we actually, in internal logic of this topos, we actually get the principles that people who do proof theory will say are the characteristic principles of modified realizability, like the axiom of choice for finite types and the independence of premise principle. So one thing I sort of criticize this topos for is that it doesn't quite, I mean, although the ideas come really from the proof theory, as sort of Fruit-Schulstra's sort of extension of this modified realizability to, say, probably second order arithmetic, it then doesn't quite, I mean, if you go to the topos, it doesn't quite validate the characteristic principles of modified realizability as Schulz valued, I would say. So, and because these are these ones, so then I think this only works if you take this extensional arrow algebra instead. So this is not quite proved. I mean, I had this, so as I mentioned before, I mean, there was this master student, Meister Fries, who basically studied a particular extensional modified realizability topos. I don't think it is exactly the one that you get from this. It's a sort of subtopos of that one for another sort of nucleus in my sense. So in fact, I think this topos has several subtoposes if you want, which probably satisfy the exact same principles. So I don't know which ones we should call the extensional modified realizability topos, but maybe it should be this one, which is the biggest in some sense, and basically in some sense follows a pattern which is both common for maybe this more intentional version and this extensional version. So yeah, that's what I wanted to say. So thank you for your attention. And here are some questions.
So we have time for questions. Thomas?
I mean, if you look at what's the tactic thing called modified realizability,
Yeah.
Then I understand you're saying there is a certain model operator built in. So, which is different from what you do it on the general level you consider. Can you give me an idea what would be the syntactic variant where the model operator is not built in?
This one.
Yeah.
In some sense, the reason why we do this is because this corresponds to this idea that there should at least be one.
So the difference is there should be at least one potential realizer.
Exactly. That's why right. That's why this is not quite right. We need to sort of modify it in such a way.
Yeah, but can this requirement, I mean, restrict to the things where there is at least one potential realizer?
Yeah.
Cannot that be formulated on the general level?
So I would say that basically means that you take so that's basically my suggestion, is that you could say, well, we just take this particular nucleus and then look at the subtop of basically corresponding. So that works sort of quite generally.
But there could be other nuclei to be considered. That's all.
Yeah, sure. Yeah. I think this one is fairly canonical. In some sense, what it does is that
Now,
it's a very canonical choice, yeah.
Yeah, this paper, I wrote a paper with Algebraic a long time ago. Then we modeled the modified realizability as internal PCA in Sierpinski topos.
Yeah.
And there that local operator you have, the local operator you have is closed, I think the closed complement of set. So set is an open subtopos of the Sierpinski topos, and this is closed, the local operator for closed complement.
Yeah.
Steve?
Do you have a notion of homomorphism of arrow algebras?
No, I don't. No, actually it's a very natural question. So, so ideally it would be something which both generalizes both, sort of locale homomorphisms and the notion of, morphisms of PCAs and stuff like that as students. But no, I haven't thought about that.
I believe that you don't go beyond with this new arrow, you don't go beyond the usual representation theorem of three-position sets, no? Because it's a general.
No, I mean,
But I'm interested to know, also maybe to you, if you use the classical logic in doing this, because it can be done characterization also for more general categories. Because, for example, for type theory, because you have three positions, you said that all three positions, right? It's not true that all three positions are based on sets. So that's why I was wondering whether you can have a more abstract representation theorem. For example, for theories which are not impredicative, it is impossible, isn't it? Constructive set theory can work, representation.
That was my main failure, which is...
Main failure?
My failure is that I wanted to have something that could be predicative, but if you use a complete lattice, you are second order. That's it.
No, but the classic constructive.
Constructive.
Does it work, the representation theory constructive with the IZF, for example?
IZF, I don't know.
I think it does.
You agree?
Yeah, I've seen the program. It is topos valid.
But Thomas, you use that.
Yeah.
You use that. The fact that actually my theorem of completeness, higher order completeness, it works in any topos plus axiom of choice. You need a bit of choice.
In any topos?
I think you need a choice. You need choice.
Thank you.
I'm pretty sure over arbitrary based topos you need something called enriched triprocess.
What?
Enriched triprocess, because you need more than this vibration video, you need some kind of way of externalizing the.
I'm very interested in this. Very interested.
The definition of nucleus, I'm just curious. Do you get something which at least looks like a narrow algebra, possibly a narrow algebra with not all of the three conditions? Can you refine it to maybe just the first and the third without the second? Have you tried that?
No, I haven't tried that.
On the J's, for instance, on the elements which are from J or something, the image of the nucleus.
I see.
Sorry. Just a comment on that question. If you remove the second condition, doesn't it make it look more like a tree nucleus rather than a nucleus?
Okay. What about his notion of a pre-nucleus?
It's a non-idempotent closure operator.
Oh.
I think it's more than just the monad. It's that stuff that Wolfgang was talking about a long time ago, right? It's between a monad and a comonad. It has one property of a comonad and one of a monad.
Need preserving and increasing.
Yes.
Okay.
Okay, I think perhaps if there are remaining questions, we can do that during lunch. Thank you.